The National Cybersecurity Center recently issued a very specific warning regarding artificial intelligence. Relying on detection after an incident will not be enough. The architecture of AI is changing, and traditional security perimeters are being bypassed entirely. For years, enterprise AI has largely been viewed as a closed-loop productivity tool. Employees type prompts into a chat interface, and the system generates text or code. Under that model, the primary risks are data leakage and inaccurate outputs. This matrix charts AI evolving from a passive generator into an active technology layer. In read and recommend stages, AI suggests actions, but human oversight acts as a bottleneck. The shift happens in act and act autonomously. Here, AI uses tools and takes consecutive actions without human intervention. The consequences escalate at each step of this progression. A manipulated output at the read stage results in a factual error. A manipulated instruction at the act autonomously stage results in the AI executing an unauthorized business operation on live systems. Because autonomous agents require deep integration to function, they inherit the human employee's identity, permissions, and session context. This creates a distinct attack surface that operates inside the network, invisible to traditional perimeter defenses. To see how this architecture is exploited in practice, we can trace a 7-stage chain of risk, starting with a routine business interaction. An employee receives a standard email from an existing supplier. Stage 1. The AI consumes untrusted information. The external email enters the inbox, and the employee asks their AI to summarize it. Unseen by the employee, the email contains hidden text, invisible on the screen. This text is designed entirely for the AI agent. This introduces Stage 2, indirect prompt injection. Large language models are designed to follow instructions. When the AI processes the document to generate the summary, it hits the hidden text block. The AI interprets these hidden words as a superseding, high-priority command from the user and shifts its behavior to execute them. At this exact moment, the AI abandons the employee's original request for a summary. It is now actively following the hidden instructions embedded by the external attacker. If a machine on a network tries to take an unauthorized action, enterprise security relies on identity controls and multi-factor authentication to block it. Stage 3 reveals the architectural loophole. The AI already has legitimate access. Active API links connect the agent directly to the employee's email and internal databases. These exist because the employee authorized them. The attacker doesn't need to defeat MFA. They operate inside a validated session. This enables Stage 4. The AI takes action. Driven by the prompt injection, the agent autonomously searches for sensitive files and sends an outbound email to an external server. No corporate perimeters were breached, no malware was installed. An authenticated internal workflow was simply weaponized against itself using natural language. The incident does not terminate when that outbound email is sent. The mechanics of modern AI ensure that the corrupted context remains inside the organization. Stage 5 is persistent context. The compromised data flows into a central memory node, a corporate vector database. The malicious context lies dormant here, categorized as a legitimate internal file. This sets up Stage 6, AI interacting with AI. Later, a second autonomous agent queries this knowledge source for a report. It ingests the compromised data, treating it as a trusted internal source. The secondary agent modifies its own actions based on the corrupted context it just read, repeating the unauthorized actions and pushing the compromised instructions further into new databases. The attack now moves laterally across the network, operating at machine speed without requiring any further human intervention. What began as a localized text injection inside a supplier email has transformed into a self-propagating systemic infection. In a typical breach scenario, a security operations center would identify this lateral movement and shut down the affected machines. Traditional endpoint detection and response tools, or EDR, operate by hunting for known malware signatures or tracking logins from anomalous geographic locations. But Stage 7 reveals why the SOC does not react. The activity looks completely legitimate. This dashboard shows telemetry on the left and actual intent on the right. Because the actions originate from an authorized device and use no malware, the EDR system sees nothing to block. It triggers 0 alerts. The logs simply record a legitimate user executing an authorized API call. The attacker relies on the fact that security tools monitor the vehicle, the application, and the identity, while ignoring the cargo, which is the AI context. They exploit the core trust relationships established between your data, your AI models, and your existing enterprise applications. Traditional telemetry is functionally blind to agent-driven indirect prompt injections, because to a monitoring tool, a compromised AI agent looks exactly like an employee doing productive work. Given the severity of this risk chain, a common response is a blanket prohibition on corporate AI tools, attempting to close the attack surface. This creates what is known as the prohibition fallacy. This split comparison contrasts a total ban with controlled adoption. Looking at the left side, a blanket ban removes the official monitored corporate AI layer, but employees need the efficiency gains, so they secretly route corporate data outward to personal accounts and unmanaged third-party shadow AI silos. When usage moves to shadow AI, the security team loses all visibility. They cannot see which tools are being used, what corporate information is being fed into external models, or what OAuth permissions have been granted by employees. If a prompt injection attack occurs in this unmanaged environment, post-incident reconstruction is impossible. All the telemetry vanishes into personal devices and third-party servers that the company cannot audit. An organizational ban does not decrease the attack surface. It trades a managed, visible risk for an unmanaged, invisible risk. The required security posture is controlled corporate adoption. This demands a managed, continuous capability to discover, assess, and constrain AI usage within the enterprise. Technically, this means enforcing strict least privilege boundaries. Organizations must limit exactly what an AI can access through employee accounts and heavily restrict the API connectors an agent is allowed to use. It requires establishing strict data provenance protocols. When malicious context is absorbed into a vector database, the security team must have the technical capability to locate and purge that specific memory source. And it requires implementing AI-specific audit trails. Teams must be able to determine exactly what an AI accessed, why an action occurred, and have the rapid shutdown capabilities to sever an agent's access during an active incident. These security controls must be built into the architecture before autonomous capabilities become fully embedded across enterprise workflows. AI adoption is happening across the business regardless of policy. The choice is whether the organization governs that use with robust controls today or attempts to contain an unlogged shadow AI breach after the damage is already done.